goes for your vestibular reactions, which basically sums up, tells you which way is up, and if your head is turning or not. In both cases, even though we're not going to talk about vestibular reactions, but in both cases, be it vestibular or hearing, they both rely on the same thing, and that is both senses encode the presence of their particular adequate stimulus by the bending of a hair. So you bear in mind, when we're talking about vision, we have all this stuff up front, the cornea, the lens, the ciliary muscles, the zonular fibers, are all setting the light up so that it hits the receptors properly, so the primary transduction process can take place. In this case, sound, since we're going to restrict ourselves to hearing, sound, which is pressure waves in air, have got to be converted and transduced into the inner part of your head in such a way that a hair is bent. And because both hearing and vestibular require the bending of a hair, they're called mechanoreceptors. Mechanical, whatever. Okay. Okay. Now, these movements are not big. As a matter of fact, you don't have to bend those hairs that we're going to talk about too much. Matter of fact, about 1 nanometer is enough of a bend to stimulate these hair, if you like, hair cells. The range of human hearing is about 20 to 20,000 hertz. If you haven't destroyed it by listening for a long period of time with excessively loud or intense sounds. And we are particularly sensitive in about the 1,000 to 4,000 range. And that also is fortuitous because a lot of human voices are in that particular range. And more numbers. Oh, by the way, doctors, I'm talking to Dr. Karpinski asked me to remind you, if you have a calculator and you want to bring it to the exam, then you're welcome to. And this is the range. And, okay, so 20 to 20,000 hertz is the frequencies you can hear. We're most sensitive 1 to 4,000. And the range of intensity, that is from soft to loud, is about 1 to 10 to this. 1 as a ratio, no, 1 to 10 to the 6, okay? Now, just a little bit about sound. We use the term decibels to discuss the sound intensity, and it's a comparator. Essentially, all you're doing is comparing a standard sound with how well you can hear it. And so, we have the decibels, the ratio of sound, whatever sound you want to talk about, compared with a standard. And so a decibel is 10 times the log, and the base 10 intensity of sound divided by the intensity of standard sound. I didn't know how to, at the time I looked this up, I didn't know how to do a line across there. And we all have other things to do, and occasionally I keep forgetting to put it in. Sound intensity is proportional to the sound intensity. So this is what a decibel sound intensity is proportional to the square of the sound pressure. So it's 20 times the log of the pressure of the sound versus the standard. And for those of you that haven't had and enjoyed physics, a dyne is the force acting continuously on a mass of 1 gram, which imparts to it an acceleration of 1 centimeter per second squared. And so this is kind of the minimum sound we think we can hear if you like to know the energy. And shear is something we'll talk about later definitions out the way down. Shear is an action or stress resulting from applied forces that cause two contiguous parts of a body to slide relatively to each other in a direction parallel to the plane of contact. It's a wonderful definition. What it means is this. That is shear. Okay? It's two forces being applied to two contiguous parts of the body. They're definitely side by side here. And they slide relative to each other in a direction parallel to the plane of contact. They're not doing this, they're doing this, right? So never say something simply that you can, really make complicated as I think the answer to most biology. Okay? So we have a definition of decibel, its intensity, also how much pressure that the sound is exerting. We have this wonderful definition of dyne. This is the amount of energy, which is the quietest sound that somebody with normal, undamaged hearing should be able to hear. And we have the concept of shear as two parts, contiguous parts of the body sliding past each other. So, so this is the standard that everything is being compared to, so it's considered 0 dyne, okay, or 0 decibels. And then as you go up, you can get some kind of a feel for the decibel concept, okay? So let's get those are some words, terms that I'll use as we go through. So we're going to do like we did with the eye. We're going to start out here at the outside and work our way in to where the action is. As you probably already know, the ear is conveniently divided up into 3 portions. We have what we call the external ear, which starts at that flappy thing on the side of your head called the pinna, moves into the tympanic membrane. Then we have an area we call the middle ear, and then we have an area called the inner ear. So we're going to start, as you would expect, with the outer ear. The outer ear does a couple of things in general, and most all of them are protective. You have, if you look at amphibians and reptiles, their eardrum's right out on the surface. You can see it just right there on the side of the head. You don't have to do any dissecting or looking or anything else. It's right there. Well, that means that it is subjected to the atmosphere, changes of humidity, being poked or prodded by twigs or sticks or something. And so it can be damaged fairly easy because it's out there on the surface. So we've moved our eardrum, our tympanic membrane, in. So it's not out here, it's back here. Now that does cause some positive things and some negative things. The positive is it's now not quite so easy to have it damaged. You have to really, get working with a Q-tip if you really want to puncture it, or a nail would work good too. But under normal conditions, it's difficult. But it also engenders a couple of some problems as well. First, it's not in a readily obvious place for sound to hit it. So you put the pinna out there, and the pinna actually focuses sound into the, you can call it the ear canal, but the $10 version is the external auditory meatus. Ear canal works well too. Depends how much you want to impress your friends and neighbors. Okay? And so the pinna here isn't designed just to hold up people's spectacles, but it actually does focus sound into the ear canal. And also helps act a bit of a baffle. It tends to promote or amplify sounds in the range of about 2,000 to 6,000 hertz. So it actually kind of preferentially selects, because of the folds and baffle that you got in here, kind of actually enhances 2,000 to 6,000 hertz sounds for you to hear. Okay. And it does focus sounds really well, except if it's directly overhead. Doesn't work too well with them. If it's a leopard standing up in the tree right above your head, it probably doesn't matter if you hear what's coming or not. But anyway. So that's the first thing. But now you've got another problem, and that is you've got this canal. It's about 25 millimeters long. Make sure I've got my units right, since I'm relying on my memory. Yes, 25 millimeters long. And you've moved it, the tympanic membrane in. Well, yes, you now have less likelihood of inadvertent injury. You've overcome the fact that it's not out there, it's readily accessible sound, focusing it into the ear canal with the pinna. But now you have a dark, moist canal. And that means that you can have a couple of things happen. You can have things crawl in. So there tends to be a few hairs, they're not in the diagram, but there tends to be a few small hairs growing in the ear canal, so that if something does crawl in, it will brush against the hair and vibrate the hair, and one tends to then start, doing things to try and extricate whatever it is that crawled in. And the other thing is, because it's warm and it's dark and it's moist, it means that fungi can grow in there as well. And so we overcome that by making something called, the $10 word is cerumen. It's the $2 version is earwax. Okay? Same thing. And the cerumen does two things. It's made by cells deep inside here. And, of course, all you have to do is turn that into an adjective. It's a ceruminous glands. These earwax glands make this stuff, push it out, and it, as it makes it, it pushes it along. New stuff at the back pushes the stuff, older stuff in the front. So it kind of sticky, and it helps pick up dirt and dust and stuff. And second, it has an acid pH. And the acid pH inhibits fungi and bacterial growth. Most bacteria and fungi do not like growing in particularly acid environments. And so, in this way, you have overcome some of the potential hazards of protecting the eardrum by moving it inside 25 millimeters. You've now got hairs and the earwax present to help protect the eardrum and to keep it, the canal clean and free of fungi and bacteria. There are parts of the world, you go down to Houston, Texas, where the humidity is extremely high, and it's very common to see people take a dropper and put a dropper or two of rubbing alcohol in there if they've been swimming a lot, to help dry out some of the water, and also to help ensure that you don't get fungi growing in your ear canal, because it can happen down there due to the high humidity. Okay, so that's the outer ear. So that brings us to the border between the outer ear and the middle ear, which is the tympanic membrane, or the eardrum, if you like. And it is the tympanic membrane's job to convert pressure waves in air, which we call sound, into something else. And that something else is mechanical, a mechanical energy. That is, it vibrates at a frequency determined by the frequency of the sound coming in, and the amount of displacement of the eardrum depends upon the intensity or loudness of the sound coming in. So whether it vibrates fast or slow depends upon what the frequency or frequencies of sound coming in to the eardrum are, and how much you see. If you could look at a cross-section of, is it doing this or is it doing this, depends upon the loudness or the intensity of the sound. very efficient at this, and very, very little of the sound energy is reflected away. So it's very effective at absorbing the energy and vibrating depending upon the frequency and intensity of the sounds coming in. Okay, well, this is just a little bit of a blow-up here of the middle ear. Here's the tympanic membrane. And attached to the tympanic membrane are three small bones, sometimes called ear ossicles. Ossicle just is a technical word for small bone. And they are very small bones indeed. They are it's up here. The malleus, the hiatus, and the stapes. Malleus means hammer, hiatus is anvil, and stapes is stirrup. For those that are not Latin fans. Okay. Now, as you can see, the malleus is attached here to the tympanic membrane, and the three little bones connect together to yet another window, another membrane that you can't see very well. It's called the oval window, and it's because the foot plate of the stapes sits right against it. So these three little ear bones sit in between two membranes, the tympanic membrane on one side and the oval window on the other. Their job is to amplify the energy coming in. When you take sound and move it from the when you take sound energy and you move it from one medium to another, a lot of it, first of all, a lot of it's reflected, and the other thing is depending on what the other medium is, it may be more viscous and take more energy to move it. If you, simplest way of doing this, you've been in a swimming pool, you're sitting up with your head above the water, you hear the sound nice, you stick your head under the water, you don't hear it so well, because as the sound is going from a less dense medium, air, into a denser medium, water, most of the energy is reflected away. Second, water is more viscous than air, and so it takes more energy to get the water to vibrate than air. And so again, you hear less when your head is underwater. It's the same sort of thing if you've got the radio playing in your bathtub and you submerge, sound goes down. But if you put the radio where it sits on the bathtub and your head's underwater, it's louder because you're getting the more direct movement of the energy from the bathtub is now starting to vibrate as well. Okay? So these three little ear ossicles tend to help promote the amplification of the sound by several mechanisms. First, everybody always looks at it right away and says, well, obviously it's a lever action. And that's true. These three little bones do act as a lever system, and will amplify the sound energy about approximately 33%. Okay. So by simple lever action, you enhance the energy going from the tympanic membrane to the oval window, the lever advantage. Secondly, you get an increase in energy because the surface area of the tympanic membrane here is much bigger than the surface area of the oval window. So if you put the same amount of energy from a large surface to a small surface, you get an amplification. In this case, it's about 20 times. Okay? So the main function of those little ear ossicles is to enhance or amplify the energy. Lever action, about 33%. difference in the surface area between the tympanic membrane and the oval window about 20 times. Oh. Now, the middle ear is also an air-filled chamber. This is filled with air, and there's a little tube that runs down and connects up with your pharynx, and it's called the eustachian tube. And this is where, when you are going up in a building, going up in an airplane, sometimes you get this kind of pressure feeling in your head, because the pressure differential between the outside on one side of the tympanic membrane and toward the inside here in the middle ear chamber are not balanced. And so if you go up, the air pressure goes down. So this side being low pressure, if this hasn't drained properly, then this air is trapped in here, and if you have high pressure, it causes the tympanic membrane to push out, and so you get that kind of congested head feeling. So sometimes you swallow or yawn or do a movement like that, and it helps pop it open. And it will quickly equalize because of the back of your pharynx, back of the back of your mouth, the pressure on both sides becomes equal and everything's fine. In the old days when they propelled in planes, they didn't have a mechanism for equalizing or building up the pressure in the cabin, and the stewardesses would, that's what we call them, like where it was more politically neutral with these stewardesses. They would pass out, have a stand there at the door of the plane with a bowl of chewing gum, so you could, because the chewing motions also popped open, so it helped equalize the pressure on both sides. Okay. Now, we also have another membrane here called the round window, and that's actually from the cochlea into the middle ear, and that is a membrane that we will see as sound energy goes into the cochlea. You have to have a way of getting rid of it. It's sort of just like we had the retinal pigment epithelium absorbing light that didn't get absorbed by the rods and cones. Well, the round window does a similar thing. Any sound energy that doesn't activate the hair cells that we'll talk about shortly goes around, and the round window vibrates and puts the energy into the middle ear where it's just dissipated, and you don't get sound bouncing around inside your cochlea, confusing things. Right? You'll also see that there are two little muscles here. They are the trivia fans. These are the two smallest bits of skeletal muscle of the body. One's called the tensor tympani, and the other is the stapedius. And these two little muscles have a protective function. In humans, the stapedius is the most important one, and it connects between the wall of the middle ear and onto the stapes there. And these little muscles, when they, and I say stapedius in humans is the most important one, what these guys do is help in a lot of little things. One is, if you've ever been to a cocktail party and you want to be talking but hearing what's going on next door, these muscles help do that because they tend to start to contract about 1/10 of a second after, well, we'll get to that in a second. And anyway, they contract about 1/10 of a second after either ear is exposed to a very loud sound. So you get the loud sound, and because of synaptic, transmission and synaptic delay, then these muscles contract. And what they do is they pull the stapes, in the case of the stapedius, it pulls the stapes about 50 micrometers from its rest position, and also stiffens up some of the tendons connecting the malleus stapes and the stapes at the same time. So by stiffening things up, it means they're not vibrating, and so you're not getting that lever action going, so you're reduced the sound. And the other thing is by moving the stapes a little away from its rest position, normally it pushes against the oval window, much like a piston. And when the stapedius contracts, it tends to cause it to have a slight door opening and closing movement. And that also means that instead of like pounding like this, it's kind of, doing that kind of little side movement, and that dissipates some of the energy as well. But it only decreases the intensity of sound by about 20 decibels. And because they're very small skeletal muscles, you can also fatigue them easily. And so exposure to loud, intense sounds will irrevocably damage the sound conducting system a little farther along. The other thing, and that's where I got ahead of myself, is these muscles also contract just prior to you vocalize it. So when you decide to say something, those PDS and to a lesser extent the tympani contract, thereby reducing the vibration and the resonance that your head makes. And so this means that you can still hear something going on around you while you talk. So you can listen into the conversation at the table next to you at the restaurant. It's more interesting than the conversation provided by your company. Okay? But it is so that, because if you didn't do that, because of the sinuses in your head and stuff, you get so much resonance that you probably wouldn't hear much of anything going on around you. So by having these muscles contract and reducing by about 20 decibels the loudness in your voice, you can hear things going on around you. Okay. So we've taken funneled the sound energy into the tympanic membrane by having the pinna focus the sound into the external auditory meatus. The tympanic membrane starts to vibrate. The vibrations of the tympanic membrane cause the inner ear oscilles, the malleus, the stapes, the malleus, stapes, and stapes to vibrate, which enhances the sound energy. The differential cross-sectional area between the tympanic membrane and the oval window further enhance the sound. We balance things off by allowing air pressure on both sides of the tympanic membrane to be equalized to the eustachian tube, and the round window is a mechanism by which we dissipate excess energy. Okay, so we've done this bit. Here's the oval window, stapes against the oval window, and here is the cochlea. So that's the cross section. Now the cochlea gets its name. Let's take the R off the end, cochlea there. Gets its name from the Latin. It's Latin for snail. Escargot. It is about 4 millimeters in diameter and is coiled up 2 3/4 turns. Okay? If you unrolled it so that it was a straight tube, it would be about 35 millimeters long. Okay? Just so you get some kind of an idea of the size of what we're dealing with. It is buried in what's called the petrous portion of the temporal bone. And as you know, petrous means stone. It's the hardest part of the skull. And when you unroll it and slice through it and look in cross-section, you would note that it looks like it's made up of 3 tubes. Stala vestibuli at the top. Sometimes this area here, they call it the cochlear duct, but sometimes called the stala media. And the bottom one is the stala tympani. In fact, the stala vestibuli and the stala tympani are one continuous tube, one very long U-shaped tube with the U being on its side. So if you look, this is the stala vestibuli, and then they have a little front as a small port together. There's trying to emphasize that it's one, the vestibular and the tympanic are one tube that are, you know, like a letter U. And this is the helical trema. And the scala media, a cochlear duct, is in between. Okay? And this is the oval window here. And this is the round window. Okay? So what we've done is we're looking, they've cut through there, and we're looking at this end on. Okay? Now, we have a membrane here. Let's see the name of this one. Same picture. Cut through the same thing, except I think it should, there it is. There is, this is the scala vestibular here, and there's a membrane here. Sometimes vestibular membrane for those that have sympathy for students trying to remember lots of names. It's also sometimes called Reiser's membrane. Okay? And it separates the scala vestibular from the cochlear duct. And then along the bottom here, there's another membrane. It's called the basilar membrane. Now the basilar membrane is not a true membrane. It's kind of a membrane made up of fibers, and it is narrow and relatively stiff near the stapes there. Oh. Brings back memories of the good old days. So it looks like that if you were to look at it from on top. So the stapes in. Can everybody see it now? Should I go ahead and turn on some lights? Okay, this end is the stapes ends. It tends to be rather narrow and relatively stiff. And as you go out farther and farther, it broadens out and it becomes broader and more limber, loose. And we will see that this graduation or gradation of mechanical properties is very important to the sound frequency analysis. Okay. Now, sitting on top of the basilar membrane is the organ of Corti, which is out all of that stuff there. Okay, so this is the basilar membrane down here, and this is the organ of Corti. And what you see is that there are, we're finally getting to those hair cells. You have a single row of inner hair cells and 3 or 4 rows of outer hair cells. So they have microvilli on their apical end here, and it is embedded in a thin gelatinous membrane called the pectoral membrane. It is that single row of hair cells that encodes sound. These, the outer hair cells have other properties that help amplify. That's kind of what the outer hair cells look like on an electron micrograph. A little bit like that sort of thing. Okay. So, be they an inner hair cell or an outer hair cell, they all tend to have their microvilli at the apical end embedded in that thin gelatinous membrane called the tectorial membrane. Okay? So a little stylized version looks something like this. Okay, here's the inner hair cells, the outer hair cells, plasma membrane, pectoral membrane. So now, what happens? Here we come to the primary transduction process. The stapes pushes against the oval window, and that generates, you now have, remember, it's a CO2 with a membrane at each end. So if you push on that, and it's completely fluid filled, when it pushes and releases, when it pushes in, it's putting energy into that fluid, and that's going to travel around vestigially and around through underneath the scala vestigially, and it's going to put movement and put pressure on either Reisner's membrane or the vascular membrane, which is going to cause it to move up and down. The whole system with the organ accordion will start to move up and down. As it does so, you're going to get that shear, remember? Business I did at the beginning. So what's going to happen is you're going to have, as that moves up and down, it's going to cause movement between the hairs on the inner and outer hair cells. We're mostly interested in inner hair cells. And the pectoral membrane, and you have just bent a hair. Okay, they're trying to show it a little better here. Here they've got it where they're trying to show that the Reisner's membrane depresses and pushes the vascular membrane down here and here, kind of tries to show it. Okay, so all you're doing is saying you push against that membrane filled with fluid, and you push it, you're putting energy into the system, and it causes the membranes to deflect. When they deflect, they move the vascular membrane, the Reisner's membrane, which causes the organ accordion to move up and down, which means you start bending these stereocilia. You have a shear force going across. And so the little hairs are, remember, they're embedded in that pectoral membrane, so they're doing this. You bent the hair. Of course, I haven't told you what that does just yet. But you will. Okay, if one now goes in and takes a good look at the what's going on in the scala tympani and scala vestigiali and the scala media, we find that in these top two, the tympani and the vestigiali, they are filled with a fluid called perilymph. This perilymph looks very much like cerebrospinal fluid, the stuff that invades your brain. Okay? The stuff inside the scala media is called endolymph. Okay, so you have a differential between the types of fluids that you've got here. Scala, vestigiali, and tympani, perilymph, very similar to cerebrospinal fluid, no big deal. Endolymph in the scala media, and it has a higher concentration of potassium and calcium than perilymph. Because of the amount of potassium and calcium in the endolymph, there's actually a voltage difference across either Reisner's membrane or the vascular membrane, about 80 millivolts. So there's a big charge difference across there, as well as concentration difference. So now, when those little hairs, okay, so we've set it up. You've got one type of fluid bathing around the scala media and a different one inside the scala media. You find that those hair cells, all in the, we're talking, these are the inner hair cells. These are the ones that are encoding sound. These are in there, in the top ear duct. Only the microvilli are exposed to the endolith. This is a very tight junction, so that the cell body is exposed to the perilymph, which is just a nice, ordinary bathing solution. But the hairs are stuck into this endolymph. And so when they start to be sheared back and forth, they actually have mechanically operated little doors, like little trap doors. It actually sees them under electron microscopy. It pops these, when they're brushed, they tend to pull, you know, but they tend to be bent toward the tallest one because they like staircase. They pop open. And if they bent the other way, they kind of close, since they're open, you know, shearing back and forth. That's not a biggie. But when they are sheared, the gates open, and potassium and calcium diffuse down their concentration gradients to polarize the cell and generate action potentials. Okay? So, by putting that pressure into the perilymph, and you bend those membranes, moving the organ of Corti as a whole up and down, and that causes a shear between the hairs, which are exposed to the endolymph, but also embedded in that pectoral membrane. And as they get, I guess this is one place where you can actually use the term get bent and not just socially inept, but these hairs do get bent, and they pop those mechanically operated channels open. The potassium and calcium flow down their concentration gradients and to polarize the cell, which again will lead to the release of excitatory transmitter, which goes and stimulates the nerve cells there that form up the cochlear division of the eighth cranial nerve, the auditory nerve, if you like. Okay? Now that's fine. We now know there's a sound out there, but we know that there's more to having a sound out there than just it's there or it's not. We also know that we can tell it's a high pitch note or a lower note. Okay? A guy named Alexander von Becassi in the 60s won the Nobel Prize for figuring out how we do frequency analysis. It was rather difficult because remember all this is encased in the hardest bone in your head. And he precipitated very tiny crystals of silver nitrate onto the basal membrane of cats here and then put in known sounds and watched through a microscope what happened. And what he found was that the mechanical gradation of the basal membrane, narrow and stiff here, wider and more limber here, was key. Because what he found was that because of the mechanical variations in the basal membrane, high frequency sounds tended to vibrate the basal membrane close to the stapes. Middle notes tended to have a predominant effect a little farther outward away from the stapes, and the bass notes tended to get maximum vibration at that broad limber region. And so what he found was that you only got these little deflections that he's shown here, here, and here in this diagram in restricted areas depending upon what sound is coming in. And so the brain knows that if hair cells at this end are getting sheared and it's generating action potentials, it interprets it as a high note. A little farther out, it's a middle note, and if it's out here, it's a bass note. And so that's how we do sound frequency analysis. Okay? Now, I had some excellent questions coming to me on email this time. There is, of course, a lot more to both vision and hearing than what I've given you. We only have 3 lectures, so I'm kind of stuck. So I have to try and give you an overview. There's a lot more to how we sharpen up these cheeks so that people with perfect pitch, you ain't going to hit 3 notes on the piano and they tell you what the 3 of them are. Well, the outer hair cells have a role there, but I don't think you want me to launch into it with 3 minutes to go, because then all I end up doing is confusing everybody. But this is supposed to be an introductory class, so I apologize if I'm not giving all of you as much as you want, or if I'm overwhelming those that have had enough. But you know, just so you know that yeah, there's more to both vision and to hearing than what I've been able to give you. All I can say is if you're in honors physiology, take 405, and you go. The whole term is nothing but sensory physiology. You'll get inundated with more videos and detail than you could possibly ever want. Anyway, if anybody has any questions, we've got a couple minutes. I'll be glad to answer them if you wish to share them with everybody. If there's something you'd like me to repeat real quick, I mean, it doesn't do me any good. I've done this a few times. Yes, ma'am. No, I would never give you a diagram saying label it all. This is supposed to be physiology, more function. And that does not mean, however, I might not ask you to draw a picture. But it wouldn't be, you know, it would be only relevant to, as a part of the answer, not draw an eyeball and label the whole thing. No, lay it behind you. Run by me and think I couldn't hear you. Yes. Remember, whether a substance depolarizes or hyperpolarizes depends upon the starting conditions. When you did the Nernst equation with a nerve, you were dealing with a certain concentration of sodium and potassium across the membrane at the beginning, which is kind of more like the similar in concentration to sodium and potassium as a paradigm. And so, yes, inflow of potassium tends to cause one set of events. But we have completely changed the starting conditions. So if you plug in concentrations in the nervous equation, you find that all those positive charges flowing in potassium and calcium will bring them up to threshold environment. And also we're going to get across that membrane a charge already being built. Voltage and initial.
I thought the Scala media was the Scala. What is it?
Yeah, so it's potassium flowing in.
See, there's the Scala vestibuli. Yeah. Is that the same as the media?
No, the media is this.
The pictorial membrane?
Yeah, like, no, basically this region.
Oh, okay.
A bit more calcium on top. So the potassium is causing the depolarization and the hairs. And just like when you have a nerve action potential coming down there, we get to the presynaptic terminal, there aren't any sodium channels and there's all calcium channels. Same sort of thing. Potassium starts causing depolarization. You have depolarization of the whole cell. That's also more calcium